as something really special. You embrace the new world of AI while also advocating for caution that is very educational. Next up, we have the brilliant Martin Lichtman, who is a zealous and optimistic explorer of light and matter. Martin's research in quantum computing sits at the boundary of atomic physics and information science. With these tools, we can both probe the nuance of our natural world and also harness its complexity to solve the big problems.
Good luck.
Our civilization is now poised to use nature's own tools to unlock that boundless potential. Martin earned his PhD here at UW-Madison, did postdoctoral work at the Joint Quantum Institute, and is now a senior quantum physicist at Inflection, a quantum hardware company that harnesses the precision of lasers and atoms for timekeeping, sensing, and computing. Martin is also passionate about Wisconsin's winters, and is a two-time age-class U.S. national champion in short-track ice speed skating. Please join me in welcoming Martin.
Good evening. I build quantum computers. We jokingly refer to ourselves as quantum mechanics. It's very difficult work because you see the atoms under the hood, they're very small, and so we need to use really tiny wrenches in order to get in there. And we never quite know the position or the velocity of all of our parts, so we're always misplacing things. It's a joke and a bit of an exaggeration, but actually not much of one, and I'll explain a little later what I mean. But these tiny machines that I work on, they're going to have a very big impact. We're poised now at the edge of two civilization-altering revolutions, one in artificial intelligence and one in quantum computing. And what I'd like to tell you about tonight is how the synergy of these two will have the greatest benefits of all to our society. So if we're going to talk about quantum computing, I'd like to get on the same page and define a few things. We need to know what is a quantum, and actually, let's take a step back and talk about what is a computer. So how would you define a computer? There could be a great deal of disagreement. Most of us think of it as this bucket of transistors that represents our desktop computer that we know and love. But you can also do computing with hydraulics or even dominoes. You can use the cogs and gears that Babbage used in his analytical indifference engines. You can use vacuum tubes like in ENIAC, or going back a little further, what about the human astronomers who were called the very first computers? Now, pick your favorite architecture. The implementation is actually just a detail. All of these have in common that they store information that we call data. And then according to some set of instructions that we call an algorithm, they transform that data step by step into new data. Now, a quantum computer can also come in many different architectures. You can have superconducting circuits. I've worked on ions that are trapped in RF fields. You can have defects in diamonds. You can use individual electrons trapped in a semiconductor called a quantum dot. You can use photons that are guided by a series of beam splitters. Or my current work and my favorite implementation, you can have neutral atoms trapped in laser beams. The architecture is just a detail. Pick your favorite one. What's important here is that all of these share the ability to store a quantum state that we call data. And then according to the laws of physics that we call an algorithm, they transform that data step by step into a new quantum state, new data. Now, if we're going to talk about the synergy of AI and quantum, let's be a little specific there too. The data can be classical or quantum, and the processor can be classical or quantum. If you have classical data on a classical processor, well, we know that as classical computing that we have today. It can still do some very impressive things. But if you have quantum data on a classical processor, typically that's very inefficient. The slowness of simulating quantum mechanics on a classical computer is actually the big motivation for why we started researching quantum computing in the first place. However, there's a really good application there, which is that classical machine learning can be applied to tuning up our quantum computers. It can be used in our noisy quantum circuits in order to mitigate that noise. And it's actually the best technique, and it's something that we actually already use every day in this research. Now, if you have classical data on a quantum processor, that's where things start to get fun. So here we have ones and zeros as the inputs and the outputs, but in between, we're using quantum superpositions, quantum interference, quantum entanglement. And in that box, that's where we have the code-breaking algorithms. And possibly more interesting and more exciting is that we have a lot of problems where we're doing calculations on large sets of matrices, Not all problems by any means, but some problems and some very important ones, and this includes many of your favorite machine learning tools, like principal components and support vector machines, all of which have a quantum speedup. The real crown jewels are in the lower right, where we have quantum data on a quantum processor. There we can do quantum simulation, and by that I mean that we use the tools of quantum mechanics in order to explore the properties of another quantum system which has never been built. We can do quantum chemistry calculations. For example, we can optimize to find more efficient ways to make fertilizer. We can find more efficient solar cells. We can aid in the discovery of room temperature superconductors, and possibly many more applications that we've never dreamed of. You see, the problem is we do not know what this technology is capable of. And that's why I believe that AI will actually have the biggest impact in that box. Because when we talk about quantum mechanics, we often use spooky language, spooky action at a distance, a lot of mysticism, and I think that that's separated our society from understanding that it's all around us. And I believe we can build AI that doesn't have that bias. For all the bias that AI will inherit, we can choose to implement it without the notion that quantum mechanics is somehow separate from our everyday world. Now, often my parents will call and they'll ask me, oh, well, how was work today? I'll say, oh, it was fine. And then they'll be like, well, what did you do at work today? And I'll say, stuff. And I know I sound like an adolescent trying to hide my emotions from them that, they couldn't possibly understand. But in this case, it's because my colleagues and I, we probe this astoundingly complicated, hidden subatomic realm, the quantum world. It's just so far from their everyday lived experience. Man, parents just don't understand. But I myself am a parent now, and I've come to realize that I owe them more of an explanation than that. And as I think about how to explain this quantum tinkering, this hidden quantum realm, I've begun to appreciate that actually it's not hidden at all. We've chosen to describe it that way. So you can add the word quantum onto anything and make it sound infinitely cool, right? Quantum information, quantum matter, quantum light, quantum finance, quantum jazz. I made the last one up, but what a smooth sound quantum jazz would be. The problem is there's no good agreement on what quantum means, and the physicists who are best poised to define it are the ones who have the biggest disagreement. You can try this yourself. If you have friends majoring in physics or chemistry or electrical engineering, ask two of them, how would you define quantum, and then take a step back and watch them argue all night. The root of this disagreement is how we've always talked about quantum mechanics as an advanced topic, that to be privileged to study it, you need to first master classical computing and then some. We start students with Newton's laws of mechanics, but we tell them, oh, well, what you're studying is not entirely correct, and yeah, we've known that for 100 years, but you're not ready for the truth. You can't handle the truth. And then we tell them the big lie. We say, oh, but quantum mechanics isn't important in our everyday macroscopic world. And we have a perfectly good explanation that we give them. We say, oh, the phases average out. And they'll be like, oh, but sir, what phases? Don't worry, child. The phases average out. These aren't the droids you're looking for. And so we're left with this situation where quantum mechanics is viewed as an esoteric and inaccessible version of mechanics, and quantum computing, as a result, is viewed as an inaccessible and esoteric version of computing. And this is a shame, and it's wrong, because quantum computing is nature's modality of computing. It's not some fancy layer that we've thought up and applied on top of classical computing. It's the way that our universe always has and fundamentally does process information. I believe that AI will help us to be able to see that. But how can we today here as humans take a step back and unlearn some of those lessons and see the quantum mechanics all around us? Well, let's start by looking around. Look at your neighbor. What color are they wearing? I'm wearing green. So you see light waves oscillating at 560 trillion oscillations per second approximately. Now, if you were paying attention in art class in kindergarten, you might remember that, well, a green pigment like that looks that way because it actually absorbs all the colors except for green. It's kind of like maybe in kindergarten, you like to spit out your green vegetables. You're picky and choosy. Well, how does a pigment get to be picky and choosy? Well, here we have our first glimpse of quantum mechanics. A pigment is a complicated molecule, but even atoms, far simplified, have very complicated spectra of the light that they will absorb and emit. They only do so in very certain lines, certain energies, certain colors. And every element has its unique fingerprint. If you use a prism and break light into its constituent colors, you'll see the bright yellow lines of sodium in a street lamp. You'll see the brilliant greens, reds, and blues of barium, strontium, and copper in fireworks. And these fingerprints are so unique that helium was actually discovered not here on Earth, but in light from the sun, where we observed spectra that didn't match any known element here on Earth. So in atomic physics, quantum computing, we use these atomic spectra to our advantage. Now you could pick any element on the periodic table, but for various engineering reasons, we pick cesium. And that gives us access to all of these discrete energy levels in cesium. Now, there's a dizzying number, actually an infinite number, and we boil that down to just 2 levels. We do that by using certain frequencies of microwaves and laser light that only gives us access to 2 energy levels and makes the rest energetically inaccessible. That's by design. Now we have just 2 levels, and we call the lowest one 0, and the next one 1. And that's how we get to computation. Starting with discrete energy absorption, going to 0s and 1s. Now, how do we work with these cesium atoms? They're very small and very hard to hold on to. Well, in my work, which is quantum computing using arrays of neutral atoms, we make a grid of laser light. The light repels these atoms, and so we can trap single atoms, 1 in each box in this laser trapping grid. And then to make a register for computation, we have an array of those atoms. And you can see at the bottom pictures of single atoms trapped in those arrays. These are our quantum bits, our qubits, and their bright or dark state is our 0 or our 1. Now, that's the data. If we want to do an algorithm, we then hit these atoms with more laser pulses. Again, very specific colors to excite or de-excite them between these specific energy levels. But the sequence of laser pulses defines the physics that is our quantum algorithm. And so, it sounds cool and it looks cool, but if you're paying attention, you might ask, well, wait, that's just still 0s and 1s. But we were promised phases. Yes, yes, child. Okay, so let's look to nature again and see where do the phases come in. So we talked about these quantized energy absorptions. Light arrives as single particles. If you have a sensitive detector, you can see a blip of a single particle of light arriving, what we call a photon. You've actually all seen this for yourself, though. You don't need fancy sensitive detectors, especially mom and dad who had analog television that didn't have as good filtering on the signals. If you've seen static snow on a television set, that's actually the arrival of single photons of radio waves that are then amplified by the circuitry and projected onto the screen. And about 1% of that is actually from the cosmic microwave background, which is fascinating to think about, that when you see that image, part of it is the afterglow of the Big Bang. And it's right there, part of our everyday world for you to see. So, but you've also heard light described as a wave. It has an amplitude, but also a phase, just like water waves and sound waves. If 2 waves arrive in phase, they interfere constructively and add. If 2 waves arrive out of phase, they interfere destructively and subtract. Can we see this in our everyday world? Absolutely. You see it in the effects of the glare from a headlight, the shimmer on an oil slick, and even how lenses in our eyeglasses focus light. But I've got a very special place that I would like you to look for it. So the next time you're fortunate enough to have sunlight behind you and rain in front of you, take a look at the rainbow. Look at the colors, and in particular, what colors and in what order. Is it just Roy G. Biv, or is there something more? Now, if you're lucky and you have a very wide display, then you can see the double rainbow, where light bounces more than once. That's on the outside of the primary rainbow. The colors are reversed. But if you look on the inside of the primary rainbow, and you're very lucky, and I've been fortunate enough to see this several times, you need water droplets that are both small and uniform in size. You can see a supernumerary rainbow, which is the colors of the rainbow repeated over and over again, usually with the greens and the purples prominently displayed. And this was one of the first pieces of evidence that an all-particle theory of light couldn't be entirely correct. Because with particles, well, they'd bounce certain times and arrive in each bow at a certain location. But with waves, you can have these sinusoidal oscillations arrive in phase and repeat so that you can have more than one location in the rainbow where they interfere constructively. So you get a repeating of the colors. Now, next time you're looking for this, I have a trick to make it easier. If you own a pair of polarized sunglasses, put them on, close one eye, turn your head to the side. The rainbow is 96% polarized light, so you can do this and filter out the background light, making the supernumerary rainbow much easier to see. Or take a trip to the National Portrait Gallery in Washington, D.C. This is the Lansdowne portrait of George Washington, the most famous picture of him. Legend has it that it was saved from a burning White House by Madison during the War of 1812. Millions of people see this portrait every year, but what I'm about to tell you, I've never found in any textbook on it. A guided tour will tell you that the rainbow in the upper right symbolizes hope for the new nation. But I hope that you look carefully and notice a clue more important than the map on the back of the Declaration of Independence. Because painted there very clearly is a supernumerary band, and this painting predates the first explanation of the phenomenon. So, which is it? Is it a particle or is it a wave? Well, I would like to empower you to reject that question. Your view of nature does not need to conform to these paradigms of classical physics. In quantum computing, we embrace this duality. Our qubits are zeros and ones, but they're not just zeros and ones. They have phase. Our qubits are two-level systems, and there are two angles that we use to describe them. And you can visualize that as a latitude and a longitude on the surface of a globe or a sphere. Now, a classical bit is a 0 or a 1. That would be at the north or south pole and nowhere in between. But a qubit with those two angles, that latitude and longitude, can have a value anywhere on the surface of that sphere. And all of that area between the north and south pole, that's what we call the quantum superposition. So quantum computing has a much higher dimensionality than classical computing. And therefore, it has a different but larger instruction set, and that's at the heart of all of the quantum speedups. So we use some very complicated apparatus in order to trap these atoms. Those atoms are quantum bits, qubits, that store data. Then we guide a series of laser pulses into the atoms, and that's our quantum algorithm. But my parents would still like to know what I do every day as a quantum mechanic. Well, these tiny atoms need an enormous amount of machinery in order to control them. We have whole tables, entire rooms filled with lasers and racks of electronics, and we have hundreds and hundreds of tiny mirrors used to direct all those laser beams to hit the atoms. And in order for any of this to work, we need to turn a lot of little tiny screws to align those laser beams to hit the atoms. And so in the end, it actually takes a tremendous amount of wrench work to be a quantum mechanic. I would like to empower all of you to see that your world is quantum mechanical. I'd like to empower the parents and the teachers in the audience to teach your children that their world is quantum mechanical. And I would like to ask the computer scientists in the audience to think about how we can train AI without the bias that quantum mechanics is somehow spooky, mystical, and apart from our everyday experience. If we can do that, we can leverage the power of the synergy between AI and quantum computing. Quantum computing will solve big problems that we have not yet dreamed of, and future generations must be free to dream. Thank you.